Problem number 91. The half-life of a pi meson at rest is this. The half-life of the pi meson when it travels with the speed this is due to the time dilation. The half-life when the pion is traveling at a speed c by 2 would be gamma times tau, where gamma is 1 divided by 1 minus square root of 1 minus v square divided by c square, and tau is the half-life at rest frame. So we put v equal to c by 2. So this thing is now 1 by square root of 1 minus 1 by 4 times tau. So option A is the correct answer. Problem 92. The Lagrangian for a particle moving in 3 dimensions is given by this. How many independent additive constants of motion exist? We note that this Lagrangian does not depend on time explicitly. That is, dl by dt is equal to 0. That means energy is conserved. Next, we perform some change of variables. Consider x plus y is equal to u and x minus y is equal to v, which gives x is equal to u plus v divided by 2 and y is equal to u minus v divided by 2. So x dot squared plus y dot squared now becomes u dot plus v dot divided by 2 whole squared plus u dot minus v dot divided by 2 whole squared, and this is equal to half u dot squared plus v dot squared. So the Lagrangian now becomes half m u dot squared plus v dot squared plus z dot squared minus k by 2 u squared plus z squared. We make another change of variable going to the cylindrical coordinate, where u squared plus z squared is equal to rho. The Lagrangian can now be written as half m rho squared plus rho phi dot whole squared plus v dot squared minus k by 2 rho squared. We notice that phi and v are cyclic coordinate, so the corresponding momenta are also conserved. So there are 3 constants of motion. One of them is energy, and other 2 are the associated momenta corresponding to the variables phi and v. So option A is the correct answer. Problem 93. Consider a particle in the region of potential this, where k and n are positive constants. The position of the unstable equilibrium is at. We need the derivative of the potentials dv by dx, that is 2kx minus 3 by 2nx squared, and the second derivative also, which is 2k minus 3nx. So to find the critical points, we equate the first derivative to 0, which gives x equal to 0 as one solution and x equal to 4k by 3n as another. We now put these values of x in the second derivative and find that d2 by dx2 at x equal to 4k by 3n is equal to 2k minus 4k, that is minus 2k, which is less than 0. So x equal to 4k by 3n is the unstable equilibrium point. So option B is the correct answer. Problem number 94. The electric and magnetic field vector components corresponding to a plane electromagnetic field propagating in vacuum respectively are this. The unit vector along the direction of propagation of the plane wave is. So the direction of the propagation can be found by calculating the cross product of E and B. So let us do that. So we calculate the cross product, and this 1 by square root of 3 and 1 by square root of 2 factors can be taken outside. So let us put the vectors. So this is 1 1 minus 1 and 1 1 rather minus 1 comma 0. If you calculate this cross product, it would be square root of 6 times minus I minus j minus 2k. So this is equal to I plus j plus 2k. So option B is the correct answer. Problem 95. Consider V is given by this is the electrostatic potential involved for a chargeless region. The Z component of the electromagnetic field Ez is this and V is 0, at the origin. So fz can be, let us look at the options. So option A says e to the power 3z. If fz is e to the power 3z, then there will not be any z dependence in the potential, so this term will be 0. So obviously ez would be 0 and v is also 0 at the origin, so option A could be one of the possibilities. Now let us look at the second option. If fz equal to this, then v would be 9x squared minus 2y squared minus 7z squared. So v is also 0 at the origin, and ez, which is given by minus dv by z dz, is also 0 at the origin. So option A and B both could be the answers.